Imagine a machine that was built in the 1970s, older than the internet, older than most people alive today, and it is currently drifting in the cold, silent darkness of interstellar space. It is moving at over 38,000 miles per hour, heading further away from home than any other object in human history. I am talking about Voyager 1, and right now, as you watch this, it is over 15.9 billion miles away from Earth. To give you an idea of how far that really is, consider this. Light, the fastest thing in the universe, takes more than 23.5 hours just to travel from Earth to that tiny spacecraft. That means if NASA sends a command right now, they have to wait until the day after tomorrow to see if it even worked. By the end of this year, in November 2026, Voyager 1 will reach a historic milestone called 1 light day. It will be so far that a message will take a full 24 hours just to reach it, and another 24 hours to come back. Now you might be wondering, how do we even talk to something that far away? I mean, your Wi-Fi probably struggles to reach your backyard, yet we are receiving data from a 48-year-old computer that is currently outside of our solar system. When I first looked into how this works, the sheer scale of the engineering blew my mind. Look, there is a very difficult truth about deep space communication. The signal Voyager sends back is incredibly weak. It leaves the spacecraft with only 23 watts of power. That is less power than the tiny light bulb inside your refrigerator. By the time that signal travels across 16 billion miles of empty space and hits Earth, it has faded so much that it is less than 1 attowatt. To put that into perspective, that is a billionth of a single watt. Picking up this signal is not like tuning into a radio station. It is like trying to hear a single whisper in the middle of a massive hurricane from 100 miles away. It sounds impossible, and yet, every single day, we are still getting data. So how is NASA doing it? The answer lies in a massive global system called the Deep Space Network. Think of the Deep Space Network as 3 massive ears placed strategically around our planet. One in the desert of California, one in the hills of Spain, and one in the Australian outback. These 3 locations are spaced about 120 degrees apart, which is a very clever setup. It means that as the Earth rotates, at least one of these stations is always facing the Voyagers. Before a signal sinks below the horizon for the scientists in California, the team in Australia is already picking it up. This global relay is the only reason we haven't lost the probes to the vastness of space. Now, when I say these stations are massive, I mean they are truly gargantuan. We are talking about radio dishes that are 70 meters wide. That is like taking a 20-story building, turning it into a giant steel bowl, and pointing it at a tiny speck in the sky. And they have to be this big because the signal we are catching is unimaginably weak. Look, when Voyager 1 transmits, it uses only about 23 watts of power. To put that in perspective, that is less power than the tiny light bulb inside your refrigerator. Now, imagine that tiny light bulb moving 15 billion miles away into the dark. By the time that signal finally reaches Earth, the energy hitting our massive antennas is less than 1 attowatt. That is a billionth of a single watt. Scientists often say that catching this signal is 20 billion times harder than powering a simple digital watch. Without the Deep Space Network, Voyager's voice would be nothing more than background noise, completely lost in the static of the universe. But the challenge isn't just about the strength of the signal. It is about the physics of time itself. Right now, Voyager 1 is so far away that we are reaching a historic milestone. It is becoming the first human-made object to be 1 full light day away from Earth. Think about that. Light is the fastest thing in the universe, and yet it takes nearly 24 hours just for a signal to travel one way. If NASA sends a command on Monday morning, they have to wait until Wednesday morning just to hear a hello back. We are literally talking to a ghost from yesterday. But as these spacecraft age, their power is fading, and NASA is having to make some heartbreaking decisions to keep the conversation going. To understand why these decisions are so critical, you have to look at what's actually keeping these machines alive. Voyager doesn't have solar panels. At 15 billion miles away, the sun is nothing more than a very bright star. It provides zero energy. Instead, each spacecraft carries 3 nuclear batteries called radioisotope thermoelectric generators, or RTGs. They generate electricity from the heat of decaying plutonium-238. But here is the terrifying catch. These batteries lose about 4 watts of power every single year. That might not sound like much. It's less than a single LED light bulb. But after nearly 50 years, the Voyagers are operating on a literal shoestring budget. Imagine trying to run your entire house, your lights, your heater, your computer, and your phone on the power of a few light bulbs. That is the reality for Voyager. To keep the transmitters working so we can still hear them, NASA engineers have had to become cosmic surgeons. One by one, they've turned off the heaters that keep the instruments warm in the freezing void. They've shut down the cameras that once gave us those iconic photos of Jupiter's Great Red Spot and Saturn's rings. As of 2024, NASA is even turning off primary science instruments, like Voyager 2's plasma science tool, just to squeeze out a few more months of life. And just recently, we almost lost Voyager 1 forever. In late 2023, the spacecraft started babbling. Instead of sending back science data, it began transmitting a repetitive, nonsensical pattern of ones and zeros. It was like a person suffering from a stroke, unable to form words. For 5 months, the mission felt like it was over. Engineers eventually realized a single chip in the flight data subsystem had failed. But you can't just send a repairman 15 billion miles away to swap a chip. What they did next was a technical miracle. They had to rewrite the spacecraft's 47-year-old code, break it into pieces, and hide those pieces in different parts of the memory bank to avoid the dead chip entirely. It was like performing open-heart surgery on a patient in another solar system, using a remote control with a 2-day delay. When the first clean signal finally hit the antennas on Earth in April 2024, the relief at NASA was overwhelming. But even with these genius hacks, the clock
through
is
that
ticking.
space every
The
single
signal
day.
is getting weaker, and
Before
the power
leaving the
is
solar
running
system,
out. This brings us to the most mind-blowing part of the story. How do we even hear a signal that weak from so far away? Think about this. Voyager 1 is currently over 15 billion miles away from Earth. That is so far that even light, the fastest thing in the universe, takes about 22.5 hours just to reach us. So when NASA sends a command, they have to wait nearly 2 full days just to hear a hello back. But the real mystery isn't just the time, it's the power. Imagine a small 23-watt light bulb. That's about the same amount of power Voyager uses to send its signal across the vast, empty ocean of space. For comparison, your smartphone uses about 3 watts, and it struggles to find a signal if you're just a few miles from a cell tower. Voyager is sending a signal from 15 billion miles away using the power of a dim refrigerator bulb. By the time that signal reaches Earth, it is spread out so much that it's unimaginably faint. We are talking about a signal strength of less than 1 attowatt. To put that in perspective, that is a billionth of a watt. It's a signal so weak that it's 20 billion times less than the power required to run a basic digital watch. So, how do we catch something that tiny? This is where the Deep Space Network, or DSN, comes in. This is a massive, global system of giant radio antennas located in 3 spots around the world: Goldstone in California, Madrid in Spain, and Canberra in Australia. These locations are strategically placed about 120 degrees apart so that as the Earth rotates, at least one station is always pointed toward Voyager. These aren't just your average satellite dishes. The largest ones are 70 meters wide. That's roughly the size of a football field. They are so sensitive that they can detect the tiniest ripple in the electromagnetic field. When the signal from Voyager is particularly weak, like it was during the recent technical glitches in early 2024, NASA uses a technique called arraying. They link multiple dishes together, essentially turning several antennas into one giant, super sensitive ear. Recently, engineers even pointed all 6 dishes at the Madrid complex toward Voyager at once, just to hear its faint whisper. But even with the world's most powerful ears listening, the communication is an agonizingly slow waiting game. Because when you send a fix to a computer 15 billion miles away, you don't just hit enter and see the result. You wait, and wait, and wait. This 45-hour round-trip delay means that every single repair mission is a high-stakes gamble with no room for error. To truly understand how difficult this is, look at the crisis that nearly killed Voyager 1 in late 2023. For 5 agonizing months, the spacecraft was sending back nothing but absolute gibberish. The signal was strong, but the data was just a repeating, meaningless pattern of ones and zeros. It was as if the probe had suddenly suffered a stroke and forgotten how to speak. For the engineers back at JPL, this was the ultimate test. They knew the spacecraft was physically fine, but its mind was broken. After months of detective work, the team decided to send what they call a poke command. This was basically a digital nudge, asking the spacecraft's computer to dump its entire memory so they could look under the hood. And then they waited. Remember, every time they sent a question, they had to wait 45 hours to see if they even got an answer. When the memory readout finally arrived, they found the culprit, a single failed memory chip. Now, on a modern computer, a single bad chip might not be a death sentence. But on Voyager, where the entire memory is less than 1% of the size of a single digital photo on your phone, it was a total disaster. This one chip held the vital code used to package all the science and engineering data for Earth. Since they couldn't physically replace a chip 15 billion miles away, they had to do something even crazier. They decided to move the code. But there was a huge problem. There wasn't a single empty spot in the memory big enough to hold the entire section of code. So the engineers had to perform what I call digital heart surgery. They sliced the code into tiny fragments and hid those pieces in different empty corners of the memory. Then, they had to rewrite the rest of the software to act like a map, telling the computer exactly where to find each piece so it could run the program seamlessly. It was a terrifying gamble. If they made even one mistake in the code, they could accidentally brick the most distant object in human history forever. But in April 2024, after nearly half a year of silence, the signal suddenly changed. Voyager 1 started speaking clearly again. It was a miracle of engineering that proved that even with technology from the 1970s, as long as we can still talk to it, we can still save it. To understand how difficult this was, you have to realize that Voyager's computers are nothing like the technology we use today. Your smartphone has billions of transistors, but Voyager 1's entire memory is less than 70 kilobytes. That is smaller than a single low-quality photo on your phone. When the signal went garbled in late 2023, NASA engineers discovered that a single memory chip, responsible for storing a portion of the flight data subsystem, had simply failed. It likely got hit by a high-energy cosmic ray, or just finally wore out after nearly 50 years in the deep, freezing cold of space. Now, normally, if a chip in your computer dies, you just replace it. But you can't exactly send a repairman 15 billion miles away. The engineers had to perform what can only be described as digital open heart surgery. They had to take the code that was stored on that dead chip and move it to a different part of the memory. But here was the massive problem. There wasn't a single empty spot left in the memory big enough to hold that whole block of code. So they did something truly genius. They broke the code into tiny pieces and hid them in various cracks and holes across the remaining healthy memory. They essentially had to rewrite the spacecraft's brain while it was hurtling through the void. But the most nerve-wracking part was the wait. Because Voyager is so far away, a radio signal traveling at the speed of light takes about 22.5 hours to reach it. That means every time the engineers sent a command, they had to wait 45 hours, nearly 2 full days, to see if the spacecraft responded. Imagine trying to fix your computer, but every time you click a button, you have to wait 45 hours to see if it worked. And then there's the signal itself. Voyager 1 transmits its data using a 23-watt transmitter. To put that in perspective, that is less power than the light bulb inside your refrigerator. By the time that tiny 23-watt signal travels across 15 billion miles, it is so incredibly weak that it's almost lost in the background noise of the universe. It arrives on Earth as a whisper that is a billion times weaker than the power needed to run a digital watch. The only way we can hear it at all is by using the Deep Space Network, which uses massive 70-meter-wide radio dishes to catch that lonely, fading voice from the stars. But as impressive as this recovery was, it didn't solve the biggest threat to Voyager's life. A threat that is slowly but surely creeping up on it every single day. That threat is the slow, inevitable death of its power source. Now, you might be wondering, if Voyager is so far from the sun, where does it get its energy? Look, out there, the sun is just a tiny, bright dot, thousands of times weaker than what we see on Earth. This makes solar panels completely useless. Instead, Voyager relies on 3 radioisotope thermoelectric generators, or RTGs. Think of these as small nuclear batteries fueled by decaying plutonium-238. When they launched in 1977, these nuclear hearts were pumping out about 470 watts of power. Today, after nearly 50 years, they're down to less than half of that. The math of survival for Voyager is honestly terrifying. Every single year, the spacecraft loses about 4 watts of power. It doesn't sound like much, but when you are billions of miles away, every single watt is a battle. To keep the mission alive, NASA engineers have become the ultimate master accountants of space. For decades, they have been playing a high-stakes game of what can we turn off next. First, they shut down the cameras, because in the darkness between stars, there was nothing left to see. Then, they did something even more extreme. They started turning off the heaters. Imagine being in the deepest, coldest part of space, near absolute zero, and turning off your own heater. It sounds like a death sentence, but Voyager's components are so incredibly well built that they've continued to function even while frozen solid. But recently, the situation reached a breaking point. In late 2024 and early 2025, the team had to make some of the most heart-wrenching calls in history. They recently shut down the plasma science instrument on Voyager 2 and the cosmic ray subsystem on Voyager 1 just to save enough energy to keep the radio transmitters humming. But don't think these machines are giving up. In early 2024, Voyager 1 suffered a major computer glitch that made it send back total gibberish for months. Most people thought the mission was over, but the engineers at JPL managed to write a software patch and beam it across 15 billion miles. It took 45 hours for the signal to travel there and back, but it actually worked. It was one of the greatest remote repairs in history. However, even with the power managed and the computers fixed, there is another silent killer waiting in the dark. And this one has nothing to do with electricity. That silent killer is something called orientation. You see, it doesn't matter how much power Voyager has or how smart its computers are if its antenna isn't pointing exactly at Earth. To talk to us, Voyager has to keep its 12-foot wide dish aimed precisely at our tiny planet across billions of miles. But here's the problem. Space isn't perfectly still. Even in the vacuum of the interstellar medium, tiny forces cause the spacecraft to slowly drift and rotate. If that antenna moves by even a fraction of a degree, its signal misses Earth entirely and disappears into the void. It's like trying to hit a bullseye with a needle from 15 miles away while standing on a moving platform. To stay aligned, Voyager uses tiny thrusters that fire in short, millisecond bursts to keep itself steady. These thrusters use a fuel called hydrazine, but after nearly 50 years, NASA noticed a terrifying trend. The spacecraft's arteries were clogging. Inside the fuel tanks, a rubber diaphragm has been slowly deteriorating with age, creating a byproduct called silicon dioxide. This gunk has been building up inside the tiny fuel tubes, some of which are now narrowed to just 0.03 millimeters. That's less than half the width of a human hair. If the fuel can't reach the thrusters, Voyager will lose its grip on its orientation, start to tumble, and we will lose contact forever. This actually led to an incredible high-stakes drama in late 2024. Voyager 1's active thrusters were so clogged they could barely stay on target. NASA had to switch back to a different set of backup thrusters that hadn't been used in years. But there was a major catch. Because Voyager is so low on power, it had long ago turned off its internal heaters to save energy. Those backup thrusters were freezing cold. If engineers tried to fire them while they were cold, they would likely crack and break instantly. They were stuck in an impossible situation. They didn't have enough power to turn the heaters back on without shutting down a vital scientific instrument, and they couldn't afford to lose any more science data. In a move of pure genius, engineers decided to turn off one of the spacecraft's main heaters for just 1 hour, risking the entire craft freezing, just to divert that power to the thruster heaters. They sent the command, and then they waited. 23 hours for the signal to reach Voyager, and another 23 hours to hear back. For nearly 2 days, the team sat in silence, not knowing if their 47-year-old explorer was still alive. When the signal finally returned, it confirmed the heaters worked, the thrusters fired, and Voyager was once again locked onto Earth. It was a victory against the odds. But as we celebrate these small miracles, we have to face a heartbreaking reality. Every time we fix a computer or swap a thruster, we are just buying a little more time. Because there is one final, inevitable limit that no engineer can fix, and it's counting down to zero right now. That limit is the power source. You see, the Voyagers don't have solar panels. They are so far from the sun that it looks like nothing more than a bright star in a pitch-black sky. Instead, they carry 3 nuclear generators called RTGs. These aren't like the batteries in your phone. They contain pellets of plutonium-238 that produce heat as they decay. That heat is converted into the electricity needed to keep the computers running and the signals flying back to Earth. But here is a truth that keeps NASA engineers up at night. Radioactive decay is inevitable. It's a law of physics that we cannot change. Every single year, the Voyagers lose about 4 watts of power. Since they launched in 1977, they've lost nearly half of their total energy. It's like a candle slowly burning down in a massive, dark room. And right now, we are reaching the very end of the wick. To keep the mission alive, engineers have been forced to play a brutal game of triage. They've already turned off the cameras, the heaters, and any non-essential systems. But lately, they've had to start cutting into the very organs of the spacecraft, the science instruments themselves. In October 2024, they made the difficult call to shut down Voyager 2's plasma science instrument. Just months later, in early 2025, Voyager 1's cosmic ray subsystem was powered down forever. These were tools that had been working for nearly half a century, providing us with data that no other human object ever could. And now, they are cold and silent. Every time they turn an instrument off, they buy a few more months, or maybe a year. The goal is to keep at least one science instrument running into the 2030s. But the clock is ticking. By 2036, it's predicted that the Voyagers will finally fall below the power level needed to even talk to us. At that point, they will still be flying, still carrying our messages, but we will never hear from them again. And the distances involved are becoming almost impossible to wrap your head around. In November 2026, Voyager 1 will reach a legendary milestone. It will be exactly 1 light day away from Earth. Think about that. Even at the speed of light, it will take 24 hours for our voice to reach the spacecraft, and another 24 hours for it to whisper back. We are witnessing the final, lonely chapters of a journey that began before many of us were even born. But what happens when those chapters finally end? Look, there is a very sad but inevitable truth we have to face. One day soon, the silence will become permanent. Right now, the Voyager team is performing a kind of interstellar triage, turning off heaters and non-essential instruments just to keep the heartbeat of these probes alive for a few more years. They are powered by decaying plutonium, losing about 4 watts of power every year. By roughly 2030, the last of the scientific instruments will likely go dark. But do not think for a second that this makes the mission a failure. In fact, just recently, Voyager 1 faced a massive computer glitch that sent back nothing but gibberish. Engineers on Earth, working with code written in the 1970s, managed to diagnose and fix the problem from 15 billion miles away. It is absolute madness when you think about it. They are literally performing remote surgery on a machine built before the invention of the internet. But eventually, the laws of physics will win. The transmitters will stop, and the deep space network will listen to nothing but the cold hiss of cosmic background radiation. However, this is where the most beautiful part of the story begins. Even when the power dies, Voyager does not stop. It becomes a ghost ship, a silent ambassador for the human race. Carrying the golden record, which is a copper disc containing the sounds of wind, rain, music, and greetings in 55 languages, Voyager will continue to drift through the Milky Way for millions, perhaps billions, of years. Long after our cities have crumbled and our names are forgotten, these two small machines will still be out there, proving that we existed, that we were curious, and that we dared to touch the stars. It is a reminder that while our physical bodies are fragile and tied to one planet, our reach is infinite. Voyager is the ultimate time capsule. If an alien civilization ever finds it, they won't see a piece of junk. They will see a message from a species that loved, dreamed, and explored. So, the next time you look up at the night sky, remember those two tiny sparks of human ingenuity sailing through the eternal dark. They are our greatest achievement. If you enjoyed this journey through the cosmos, make sure to hit that subscribe button and share this video. We have so many more mysteries of the universe to explore together. Thank you for watching, and as always, keep looking up.